Have you ever really stopped to think about the air around you? I mean, it just feels like nothing, right? Empty space. But the truth is, it's this incredibly chaotic, invisible world. It's a frantic dance of countless tiny particles, and it's all governed by some surprisingly elegant rules. Today, we're going to pull back the curtain and uncover that hidden world.
So, that's the big question, isn't it? What are these hidden rules that control the very air we're breathing right now? How on earth can we predict the behavior of something we can't even see? Well, let's find out.
When scientists want to tackle something really complex, they don't just jump into the deep end. They start with a simplification, a perfect model that doesn't actually exist. We're going to call it the perfect gas myth. Yeah, to get to the truth, we're going to start with a simple, elegant lie. And that elegant lie is what we call an ideal gas. Just think of it as this perfect theoretical gas that follows all the rules, no questions asked, without any of the messy stuff from the real world. It's the absolute perfect place to start our journey.
So what makes a gas ideal? Well, you have to imagine two things that are frankly impossible. First, its molecules are just points in space. They have zero size. Poof! And second, they don't interact with each other at all. No pulling, no pushing. They're like perfect little ghosts just bouncing around, completely ignoring each other.
Okay, so because these theoretical particles are so ridiculously simple, they follow a set of rules that are just beautifully simple. So let's look at these rules of behavior and see exactly how our perfect imaginary gases play by the book.
First on the list is Boyle's law. It's pretty straightforward. If you keep the temperature the same, pressure and volume are opposites. You squeeze a gas, increasing the pressure, and what happens? The volume has to shrink. Give it more room, the pressure drops. Simple as that. And if you plot this out, you get this really elegant, predictable curve. It's not just theory, you see this every day. Ever push the plunger on a sealed syringe? As you push harder, the volume inside gets smaller. That's it. That's Boyle's law right there in your hand.
All right, so what happens if we switch things up? This time, let's keep the pressure the same and play with the temperature. That brings us to Charles' law, and this one's a direct relationship. You heat a gas, it expands. You cool it down, it contracts. Volume just follows whatever the temperature does.
And check this out. The graph is a perfect straight line. It's so clean. This is exactly why a balloon suddenly looks a little bigger when you take it from a cool room out into the hot sun. The temperature of the air inside goes up, and so does its volume. Okay, one more for our core set of rules. This one's from Gay-Lussac. Now, imagine a totally sealed, rigid container. The volume can't change. What happens if you start heating the gas inside? Well, those particles start moving faster, they smack into the walls harder and more often, and the pressure goes way up. And surprise, surprise, it's another simple direct relationship. You crank up the heat, the pressure goes right up with it. The pressure cooker is the perfect example of this. You're using this very law, cranking up the temperature of the water vapor in a sealed pot to build up pressure and cook your food way faster.
Okay, so this all sounds amazing, right? Simple, elegant, predictable, maybe a little too good to be true? Well, yeah, because of course the real world is messy, and this is where our perfect little story takes a sharp turn. This is when gases get real, the moment our beautiful model starts to break.
So it forces us to ask, right? These laws are perfect, on paper. But what happens out here, in the real world? What about the actual air in this room? Why doesn't our perfect model work all the time? So what gives? Where does the model break down? Well, it all comes back to those two impossible things we agreed to ignore at the start. In the real world, molecules aren't just points, they take up space. And they absolutely push and pull on each other. Those two little facts are what separate our neat, tidy model from the messy truth.
So, to deal with this real-world messiness, scientists had to level up their math. They used more complex formulas, like the famous van der Waals equation. It's basically the simple gas law, but with added correction factors to account for, you guessed it, the real size of molecules and the forces between them.
So how do we connect the dots between our perfect little model and the chaotic reality? We have to zoom in. I mean, way, way in. Welcome to the microscopic dance. This is where we finally get to the why behind all of it. This is it, the kinetic theory of gases. It's not just one rule, it's a whole set of ideas or postulates that describe what's happening on a microscopic level.
It paints this incredible picture of a gas as just a bajillion tiny particles zipping around in straight lines, bouncing off each other in the walls like perfect little billiard balls. It's a more grown-up version of our ideal gas model, but this time it's here to explain why those laws actually work.
And this, right here, is the big, mind-blowing reveal. What actually is temperature? Kinetic theory tells us it's just a measurement of the average energy of motion of all those tiny particles. When you touch a hot cup of coffee, what you're feeling is the frantic, high-speed energy of trillions of molecules. Hot just means fast, cold just means slow. It's that simple and that profound.
Once you get that temperature is just motion, it changes everything. It opens up this whole new way of seeing the world. So let's dive into this energy of the unseen and talk about what this really means for speed, for chaos, and even for the idea of absolute cold.
Now, it's easy to talk about the average speed of these molecules, but that's only part of the picture. In any gas, at any moment, you've got this whole range of speeds. You've got your slowpokes, a big crowd moving around the most likely speed, and then you have these absolute speed demons way out on the tail end. It's pure, beautiful, organized chaos.
So with all these billions of particles bouncing around, you might wonder, how is all that energy shared? Is it a free-for-all? Well, not exactly. That's where something called the law of equal partition of energy comes in. And it basically says that, in a stable system, nature's pretty fair. The energy gets distributed democratically among all the different ways a molecule can move and store it.
What does that even mean, ways a molecule can move? Well, think about it. A simple single-atom gas like helium, it can only move up and down, left and right, forward and back. That's it. 3 degrees of freedom. But a 2-atom molecule, like the oxygen we breathe, it can do all that, plus it can tumble and rotate. More complex molecules can even stretch and vibrate. Each one of those is like a little pocket for the molecule to store some energy.
Okay, so let's take this idea and run with it all the way to the end. If heat is motion, what happens when you remove all of the heat? When you get colder and colder and colder, eventually you hit a final floor. You get to absolute zero. That's minus 273 degrees Celsius, the theoretical point where all molecular motion just stops. The ultimate cosmic stillness.
And that leaves us with one last, truly mind-bending question to chew on. If absolute zero is the point where all molecular motion, the very thing that defines thermal energy, grinds to a complete halt, what does that really mean for the fundamental nature of energy? Or maybe even for time itself?